For this screencast, we're going to look at the combined gas law and some seemingly random things. Okay. So next we're going to see, really the combined law is kind of looking at Boyle's and Charles's law combined. But first, you're not really required to know about Avogadro's law, but I think it helps, and I think that it's really directly related to K&T theory, so it's not that difficult to kind of just know that it exists. Okay. In this law, the law states that the volume of a gas is directly related to the number of particles of gas. Pressure, meaning pressure outside the cylinder, is constant, and the temperature of the system's constant. Okay, now remember, N is really just related to the number of particles. And it's in units of something called moles. And we will learn more about moles as the year goes on. So if I have a certain number of particles, 1 mole, in a container, and the volume is 1 liter, if I add twice as many particles, 2 moles, remember those particles, same temperature, moving at the same average speed, they're all the same particle, okay? It's going to increase the number of collisions against the walls. It's going to increase the pressure inside the cylinder. The cylinder is going to move up until the pressure inside is equal to the pressure outside, atmospheric pressure. Twice as many particles, twice as much volume, so that the pressures are equal inside and outside the container. All right, so as the number of particles go up, the volume increases. Another random thing I'm going to throw in is called STP. It is the standard pressure and standard temperature for a sample of gas. It's chosen so that scientists can have a common reference point for gases. The standard temperature is 0 degrees Celsius, okay, and the Kelvin is in 273 for standard temperature. For standard pressure, 760 millimeters mercury, 1 atmosphere, 101.3 kilopascals. Okay. And remember, when we deal with temperature in gases, we must use the Kelvin temperature, which is 273 plus the whatever the degrees are in Celsius. So to convert to Kelvin, temperature in Kelvin is equal to my temperature in degrees Celsius plus 273. All right, so now let's get to the combined gas law. If you look at just the top here, P1 times V1 equal to P2 times V2, that's Boyle's law. V1 over T1, V2 over T2, that's Charles's law. Okay, this is maybe a simplified form, might help you do the math, particularly when you have to set the equation equal to T2. Right, so combined gas law, P1 V1 over T1 equal P2 V2 over T2. Okay. And again, it's just really combining Boyle's law, Charles' law, Gay-Lussac's law, which we didn't talk about, but that is just pressure and temperature, and then N, the number of particles, is constant, so the sample of gas remains the same between condition 1 and condition 2. All right, so let's look at how to solve these problems. How I look at, if I'm reading a problem, it says a sample of helium gas has a volume, a pressure, and a temperature. They're giving me quantities for all 3 variables that I know can be applied to gases. So in my head I go, oh wait, it's all 3, this must be a combined gas law. I get sometimes lost as to what is condition set 1 and what is condition set 2. So immediately I make this kind of little chart. Okay, pressure 1, it has a volume of 0.180 liters. It has a pressure of 0.800 atmospheres and a temperature of 29 degrees Celsius. Ooh, but I remember that I can't leave it as 29. I have to add 273 to it. So that will be 302 Kelvin. In my second set, 90 milliliters, and a pressure of 3.2 atmospheres. Now I look at these and say, okay, atmospheres, atmospheres, those are the same units. This is liters, this is milliliters. So I am going to change up milliliters to liters. Doing the math, I get that liters, and the problem asks me what temperature. So I'm looking for this. So I know that combined gas law is this equation. I want to solve for T2. First thing I need to do is get this on top. So I'm going to multiply both sides by T2. These cancel. I get T2 P1 V1 over T1 is equal to P2 V2. I want to cancel out P1 and V1, so I'm going to divide both sides by P1 V1. I want to get rid of this T1, so I have to bring it up, so I'm going to multiply both sides by T1. P1s cancel out, V1s cancel out, T1s cancel out on this side. I end up with T2 is equal to P2 V2 T1 over P1 V1. Now all I have to do is look up here in my table and substitute things in. So I have 3.20 atmospheres times my volume of liters times my temperature 1, which is 302 Kelvin, over P1, which is 0.80 atmospheres, times 0.180 liters. In my calculator, I put 3.2 times 0.09 times 302 divided by 0.8 divided by 0.180. The answer I get is 604 Kelvin. If I subtract 273 from it, I will get 331 degrees Celsius. Well, let's look. Does that make sense? That's really high. Yeah, but if you look up here, my pressure increased 4 times. My volume halved. Okay, so pressure increasing by 4 would drive the temperature way up. The volume decreasing would drive the temperature down, but not as much as that pressure, because the pressure is the largest change. So I guess that makes sense. Okay, here's another problem. Please pause the screencast, and when you come back, the answer should be up. Pause the screencast. Okay, so here's my setup, my little table up here. Notice I had to do some conversion for the one pressure. I have my equation solved for terms of V2. I plugged in my values, multiplied everything up top, divided by 1.06, divided by 308, and I end up with 313 milliliters. One thing you want to make sure of is that your units cancel. Atmospheres with atmospheres, Kelvin with Kelvin. Units left are milliliters. They go into my answer. I do expect to see this work when you solve these problems. This up here makes it absolutely clear what you did. This is worth points. You don't necessarily have to show it, but if you get anything wrong down here and I don't see this up here, I can't give you partial credit for anything like converting units so that all the units agree, for anything like converting temperature, to identifying the correct variables. Okay, so show your work, always a good thing. That's the combined gas law. Hopefully that all is good.